Alright, so this is going to be picking up right where the other one left off, and this is going to start with section 4.4. This is the first actual introduction of sine and cosine as functions rather than as sort of descriptors of a right triangle. So, if we have a circle and we have the positive x-axis and we have some line which is angle theta from that, if we change theta so that it just sort of becomes different angles at different times, we might wonder, how does sine and cosine change with that? Basically, we know that the side lengths of a right triangle have a constant ratio to each other given one of the angles on the inside. That's the definition of sine, cosine, and tangent. However, on the unit circle, we have fixed the hypotenuse to be length 1, which means the other two lengths are automatically given. So, on the unit circle, the sine and cosine values actually do not depend on the side lengths of the triangle. Instead, they depend solely on the angle. Which means we can basically say what is sine of theta and what is cosine of theta as theta changes. So now, we're thinking about sine and cosine as sort of the output of something rather than being a ratio. And so as this angle sort of walks its way around a full rotation, we're going to get different answers for these things, sort of virtually as if we had triangles with the right values to produce that hypotenuse and that angle. Since on the unit circle, where these angles intersect, we have the x and y coordinates are the cosine of theta and the sine of theta. Effectively, if I were to say, all right, f of x is sine of x, where the transition from theta to x really is just like a notation thing. A variable is a variable, so it doesn't matter if I call it t or w or h or smiley face or theta. So since on the Cartesian coordinate system the inputs are from the x-axis, I'm just switching to using x. What this is going to give us though is, since sine represents the y-coordinate of this point, as this angle sweeps out a full circle, this y value is going to change over time. And so we can say that the sine of x sort of gives us the y coordinate of a point that's walking around a circle. Likewise, we have g of x equals cosine of x. Then this is the same thing. It's going to give us the y-coordinate of a point walking around a circle. And importantly, the point, when x is the same for these, will have this exact coordinate system. So sine of x is going to be the y value of a point, and cosine of x is going to be the x value of that same point. This lets us look at something winding around a circle as sort of being broken up into, there's a function which determines its y value and there's a function which determines its x value. And so it's actually quite common to write these not as f and g, but as x of t and y of t, because if I want to have a function which sort of reproduces a point moving in a circle, I can use sine and cosine to define the position of that point. And so I have a function in one variable which tells me what the x value is. This would be cosine of t. And I have a function which tells me what the y value is, and this is given by sine of t. And so if I have a point defined as being x of t comma y of t, then for a single number t, I can produce a number, and I'm guaranteed that when I look at those numbers as a coordinate pair, it'll be a point on this circle. This concept is called finding parameters for a system. So the parameter in this case is t. This is exactly the same as thinking about describing sine and cosine as a point moving, just sort of in reverse, right? So over here we have cosine of theta, sine of theta, and it describes a point on the unit circle. Here we have, well, since x of t is cosine and y of t is sine, we still have the exact same thing. So looking at it in one way, we say there's a point winding around a circle, what described it? And the other way is to say, what do I need to produce a point winding around the circle? It's all the same math. But it allows us to look at the sort of x-coordinate and the y-coordinate of a point winding around a circle separately. And a natural question is, what does that look like? We have some viewing window here, and we have the plot of sine. Right, so this is sine of x. These are not really necessary anymore. This is the graph of sine of x. And we can see that since the x-axis is denoting our angle, of course in radians, at 0, at x equals 0, we plug that in to sine and we get sine of 0. And if we look at the unit circle, at 0, there's no height, right? A point on the unit circle at angle 0 has no height to it. And that makes sense because all of the height is in the x direction. The coordinate at that point is 1, 0 because the y value is 0. And so sine of 0 is just going to be the y value at that point, which is 0. And we see that indeed at x equals 0, the output, the height of this function is exactly 0. And so these check out. We can notice quite a few things about this graph though. One that you might notice is that it repeats, right? I'm only showing it for this viewing window, but in fact it does repeat infinitely in both directions. And this kind of behavior is called periodicity, or this function has a period to it. The way it's formally defined is a function has a period if f of x plus t equals f of x for some value t. Basically, we know that when we add or subtract something from the x term in a function, it shifts things along the x-axis by some amount. We saw this with parabolas, we saw this with circles, we saw this with all kinds of different functions. Messing with the x term moves it back or forward on the x-axis, just as adding terms on the end messes with the y value and shifts it up or down. So what this is telling us is if you shift f by some amount, it doesn't look any different, which means I can take the function and do this to it, and it looks the same. It's the same as having what's called translational symmetry. So we've talked about lots of symmetries before, like rotation about the origin or reflection about different lines. This is translational symmetry, where translation, in this case, has nothing to do with language. It actually means a physical motion around space. So when we translate this function over by some amount t, it looks the same, which is the definition of a symmetry. So this is the definition of it, and what we might want to ask is, what is the t value for sine? Right? This t value winds up being how we define the period of the function, because that sort of defines how far you have to go before it starts repeating. So sine of x plus t equals sine of x. What is t? We know that sine is a periodic function, but when does it start repeating itself? And if we look back at the geometric origin of this graph, it comes from the unit circle, right? It comes from winding this angle around the circle. And so, clearly, whenever it starts here and comes back here, it's going to give the same outputs. So, since we are measuring angles in radians, we see that sine is going to repeat every 2 pi radians, right? Once around the circumference. And so if we look here, we see that the next time we have a line like this passing through the x-axis is over here. Right? We have it here, but the line's going the other way, so it's not the same. So this point is at 0. This point must be at x equals 2 pi, right? Because that's the period of the sine function. And if we were to look at this like on Desmos or in the notes that I have, it's kind of hard to see, but that position takes place right after 6, right? Like 6 is somewhere around here. And that makes sense because 2 pi is about 6.28. And so the period should go just a little bit beyond 6 on the x-axis. And so that means we can say, because it's going to repeat every time it winds around the circle, and winding around the circle is the same as changing the angle by 2 pi, then we know that the sine of x plus 2 pi is just sine again, which is also a way that we can figure things out. This is effectively the same thing we were doing when we had like an angle of 420 degrees. We subtracted 2 pi from it because we know that it's going to be equivalent to something else on the circle between 0 and 2 pi. This is exactly that property, just viewed sort of unwound. You can also think about the plot of sine of x as if you were to have a wheel that was rolling along, well, rotating and moving, then the point, if you like fixed a single point on that circle and watched where it traces out in space, it's going to be exactly a sine curve. Another thing that we can see is, well, we can take a look at cosine of x. We look at, so I'm just going to redraw the unit circle here. If we look at cosine of x, then we get a very similar picture, but it is slightly different. Right? So, this looks, just lost my marker. This looks very, very similar to sine of x, and that's not a mistake. It's because this value, right, so at x equals 0, we're up here, and it corresponds to this angle, which gives us the point 1, 0. And so when we ask for the the cosine of an angle, it's the same as asking what is the x value of that point on the unit circle. I understand that there's a lot of translations between diagram to diagram going on and actually using the variable x more than once. So I just want to restate exactly what I said in case people kind of missed it the first time. We have a point on the unit circle given by an angle. I'm going to call that angle x and denote it using the x-axis here. And cosine of that angle x is going to be this value in the coordinate pair on the unit circle for that angle. It just so happens that on the unit circle, we call that value the x value. So just to not have any confusion, here x means the angle. Here, x means the coordinate. I know, this stuff wasn't really put together with ease and intuition in mind, but it is what it is. It's been around for longer than UVM, so yeah. We can also see that when x equals 0, we're going to get 1. And so we see that this point here has to be 1 on the y-axis. Oh shoot, can you see that? That is super small. When x equals 0, y equals 1, the output. Cosine of x, cosine of 1, cosine of 0 is 1. So, whereas sine started at 0, cosine starts at 1. This is one way to differentiate the two from each other, because if you're given two periodic curves that look the same, you can tell which one is sine and which one is cosine by where they start. Sine starts at 0, 0, cosine starts at 0, 1. And if we look at this, we can see that it's also periodic, right? The graph of cosine is periodic because it also repeats itself as it winds itself around the unit circle. So it has the same period as sine. This lets us say that cosine of x plus 2 pi equals cosine of x, right? We can shift it or translate it by 2 pi in any direction. Well, not up or down, but right or left, and it'll look exactly the same. We can also see that since this is 1, and when it wraps all the way around to pi, this coordinate is negative 1, 0, then when this goes exactly pi around, this should be negative 1. And in fact, we find that everything given by cosine of x or sine of x will be bounded between negative 1 and 1. So we can write that as negative 1 less than or equal to sine of x less than or equal to 1, and negative 1 less than or equal to cosine of x less than or equal to 1. And this is not this is not like an inequality I'm asking you to solve. Rather, this is a statement of a fact. For all x, the sine of x and the cosine of x will be between 1 and negative 1. This is going to be important when we come to sort of building functions out of trig functions, because this is called the amplitude, or rather half of the bound is the amplitude. So regular sine and cosine have an amplitude of 1 because the highest they can ever get to is 1 and the lowest they can ever get to is negative 1. If instead we wanted a sine curve whose highest point was 5 and whose lowest point was negative, well, we could do something to change that, but we're not really there yet. Another thing, so another thing that happens is simply because these things are defined on the unit circle, which is inextricably connected to right triangles, and in fact sine and cosine form two legs of a right triangle, we have another little identity, which is, well, we know x squared plus y squared equals 1, because the hypotenuse is always 1 on the unit circle. X is given by the cosine. So cosine of theta squared plus y, which is sine of the angle, sine of theta squared is always 1. And this is just because cosine and sine form the legs of the right triangle on the unit circle, and the unit circle always has a radius of 1, which is the hypotenuse. So cosine squared plus sine squared equals 1. And just as with the arc length of a circular sector or the area of a circular sector, this is another one of these identities that you should really just commit to memory. Like SOHCAHTOA. You don't have to memorize, all right, sine is opposite over hypotenuse. You just remember the mnemonic. But in this case, cosine squared plus sine squared equals 1 is very useful, especially if you go on to do calculus or Calc 2 or even Calc 3, where you have triple integrals over polar coordinates with nasty stuff. You might need to remember, oh shoot, which one is it? Is it secant squared minus 1 equals tangent squared, or the other way around? And you don't have to memorize anything other than this formula. I'm not going to tell you how it's used because that's way beyond the topic of this class, but if you commit this to memory now, you will thank yourself later. Okay, there's another thing which is, I wasn't actually going to cover this until I looked at the homework for this week, and it uses it, so there's something called a reference number. And a reference number is like a quick way to find what the coordinates are for a given angle given what that angle is sort of looks like. So if we have our unit circle and we say, all right, here's an angle, again, always from the positive x-axis, of 5 pi over 4. And so to say what is the reference number, that's going to be the smallest angle you can form with the x-axis. So to reiterate, we always define angles measured from the positive x-axis. However, we are not talking about the positive x-axis here, and we're not talking about clockwise or counterclockwise. We are only saying what is the smallest angle with the x-axis you can make. And in this case, I can make a smaller smaller angle than this if I just go straight to the negative x values, right? So this angle is going to be the smallest one that I can make using this angle and the x-axis in general. In fact, it goes counterclockwise, or depending on how you look at it, counterclockwise or clockwise, but it definitely doesn't measure it from the positive x. And so this is the reference number. What is that angle? The smallest angle you can build with the x-axis. And so this is going to be, well, kind of by symmetry, we know that this is pi over 4. And we add another pi over 4, and then we add another pi over 4, and another pi over 4, and another pi over 4, right? For a total of 5, because we are at 5 pi over 4. When we go all the way to here, and then we add another pi over 4, we get to there. So we know that this angle is just pi over 4. And so the reference number for 5 pi over 4 is going to be pi over 4. I feel like I'm saying that so many times. But the point with the reference number is that now you can figure out what the coordinates are for this point without having to do any kind of geometric stuff. We know that the coordinates for pi over 4 are root 2 over 2 and root 2 over 2. And since we know that, and we know which quadrant 5 pi over 4 is in, then we can just keep in mind which one of these has to become negative in order to talk about this quadrant. Since quadrant 3, so right, we have quadrant 1, 2, 3, and quadrant 4. In quadrant 1, both x and y are positive. In quadrant 2, x is negative, but y is positive. In quadrant 3, both x and y are negative. And in quadrant 4, y is negative while x is positive. What that means is, depending on where our angle falls and what its reference number are, we can just figure out what its coordinates have to be. Because pi over 4 has these two, and we are in quadrant 3, I know that 5 pi over 4 is going to have the same coordinates, just the negative version of them. So this is going to be negative root 2 over 2, negative root 2 over 2. And this is the idea of reference numbers, is that if you sort of reduce all angles to just the ones that are in the first quadrant, then you can sort of mirror, rotate, and flip them until you get to the angle you're actually talking about. And those only involve changing the signs, either positive or negative, on these coordinates. So let's do another one. Let's say this one, which is going to be So this is 5 pi over 3. Sorry, I had to count that out in my head. 5 pi over 3 lands in quadrant 4, so I know whatever the coordinates are going to be, the x coordinate is going to be the same, and the y coordinate is going to be negative. So before we do anything, I know this is what the coordinates are going to look like. Then we say, what is the reference number for this angle? That's going to be the smallest angle you can form with the x-axis. So I see I could go this way and form this angle. I could go this way and form this giant angle, or I can go this way and form this angle. And that turns out to be the smallest. So now, looking at this angle, we can see that this is going to be, well, we go pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. And so the last distance would be 6 pi over 3, right, to go and complete the circle. And so what that means is, because we're exactly pi over 3 away from completing the full 2 pi, this angle must itself be pi over 3. And so now we can use what we know about the coordinates of pi over 3, which are that the x value is 1/2 and the y value is root 3 over 2. And because this and this are sort of related by this idea, that means that the coordinates for this are going to be the same as this, just adjusted to be in quadrant 4, which I have already done. So now all I have to do is put it in, and I'm good to go. So there's quite a few questions on the homework, which is all about using reference numbers, and so you can think about them in this idea of the smallest angle you can form with the x-axis, or if you're a little bit careful, you can actually use a bigger shortcut, which you may have already noticed just as we're going. So when we had 5 pi over 4, the reference number turned out to be pi over 4. When we had 5 pi over 3, the reference number turned out to be pi over 3. They always seem to depend on the denominator, right? And indeed, if we had, oh geez, this is getting, okay, this angle, right, so, sorry, the angle between these two going this way, well, this is pi over 2, this is pi, this must be 3 pi over 2. And so, what's the reference number for this? The reference number for this is going to be the smallest angle you can form with the x-axis, and so it actually doesn't matter which way you go for this. To make an angle with the x-axis, it's always going to wind up being a 90-degree angle, which is pi over 2. And so we get that this one is also seemingly dependent on nothing more than the denominator. So the reference number, and this is with a little air quotes here, is generally defined purely by the denominator of the angle. This is not always true, so it's always true if the angle is in simplest form. But if I have something like 21 pi over 3, this is not in simplest form. This is actually the same as 7 pi. However, if we were to blindly apply our, oh, it only depends on the denominator rule, I would get that the reference number for this is pi over 3, right? The one that shares the denominator of 3. But this is not correct. In fact, the reference number for this, since this denominator is 1, we get that this is in simplest form, and so this should be pi over 1. Or just pi. But, so as long as the angle is in simplest form, meaning you can't cancel anything in the top and bottom, then the reference number is just going to be pi over the denominator. So I'll write that out more explicitly as if theta equals, I don't know, a pi over b, then the reference number of theta is just going to be pi over b, if they're in simplest terms. So the homework definitely asks about this because I took a look at it when I was building it. But the reference number is actually a really simple idea. You just have to figure out, like, the usefulness of the number is more complicated than the definition of the number. So I just wanted to go over that you can actually use a very, very simple rule for finding the reference number, and then if you know where or which quadrant your angle is in, you just adjust the reference number's coordinates depending on which quadrant. So as another example, if we did 11 pi over 6, this is in simplest form, and so I know that the reference number is going to be pi over 6. And then, where is 11 pi over 6? Well, we can count it out. We go pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, pi. 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. So it's going to be somewhere in here, which is in the fourth quadrant. So I know that this thing is going to have, can everyone see that? Yes. This is going to have a negative y coordinate, but a positive x coordinate, and the rest are just going to match this, which was root 3 over 2 and 1/2. So, this is just about everything I have from sections 4.3 and 4.4. Definitely this is everything you're going to need to do the homework for this week, but I would encourage you to maybe come up with some more practice problems on your own, or if you're still confused by this, please absolutely reach out to me on Campus Wire. Please make your questions public so that everyone can read and benefit from them. If you have something else going on, email me directly. I am literally at my computer working all day, so I'm going to get back to you as fast as I can. There were questions about the final. The final is going to be 2 weeks from this Thursday, right? So it is still set to be May 7th. It is only going to cover chapter 4. So it's only going to cover trig. You don't have to worry about remembering rational polynomials or horizontal asymptotes or, composition or any of that stuff from previous sections. It's only covering chapter 4. That being said, chapter 4 is the largest chapter that we're covering this semester. It has 9 sections. So far, we've done 4 of them. What this means is next week, you're going to get a bunch more sections and many, many more notes. I apologize for that. It's just the way things shook out with the pandemic. Everybody's timeline got shifted a bit. So it is what it is. But the final is still set to be on May 7th. Obviously, because you don't have to come into the classroom, it's not going to be at 7:30 in the morning. Instead, it's going to be like the midterm, where it's going to be a web-assigned homework that's just very long, and you'll have all day on May 7th to complete it. I do not, as of now, have any extra credit for this section of the class, but if that is something that people would like, I can easily come up with some more work. So I think only 4 or 5 people did the extra credit for last time. But again, if there is demand, I will supply. Obviously, this is where I'd ask if there are any questions, but you know the deal. So that's it.